The idea of a generation ship, an entire civilization travelling through the vast emptiness of deep space, captures our imagination like nothing else. But beneath the awe-inspiring vision lies a brutal reality: radiation, failing machines, dwindling resources, and the fragile nature of human society weave together into an unstoppable web of failure. This isn't just a challenge for the future, it's a fantasy built to fall apart. Let's break down why a generation ship will never survive the journey. The truth is, deep space is not empty. It's not a vacuum you pass through safely. Once you leave Earth's magnetic field, you don't just enter space, you enter a storm, a constant and invisible one. This storm comes from all directions. It is made of radiation, a steady background of deadly particles that never stops. NASA calls it a transit exposure when you are moving through it. Their data shows a representative daily dose would be about 1.5 millisieverts. That is 50 times higher than what people receive on Earth in the same amount of time, over weeks, months, years. It adds up. And generation ships measure survival not in years, but in lifetimes. The damage compounds day after day, generation after generation. This radiation exposure isn't just inconvenient, it's mission-defining. On Earth, radiation is something we treat as a problem when it happens occasionally. A nuclear accident, a medical emergency. In deep space, radiation is not an emergency, it's a permanent fact. The ship is not crossing a gap of open nothingness. It's travelling through an endless tiny hailstorm of supercharged particles. Every single one of them comes with enough energy to tear through a protective shield or disrupt a biological system. This hailstorm has a formal name: galactic cosmic rays. These are not ordinary particles, they are high-energy fragments of atoms that move faster than you can imagine. They come from deep space, from sources like supernova explosions or black holes. They pass through objects as if they weren't even there. A galactic cosmic ray could hit you, pass through your body, and keep speeding into the distance without slowing down. Shielding can block some low-energy particles. It can absorb some impacts. But these high-energy ones, especially the nuclei, are a whole different problem. The trade is vicious. To block them completely, you'd need shielding so thick and so dense that it breaks the mission itself. It makes the ship too heavy to get anywhere. That trade problem doesn't just show up once, it's the heart of this entire system. Radiation can't be ignored. It also can't be completely controlled. A voyage across interstellar space might take thousands of years. Even with incredible technology, the background of galactic cosmic rays does not go away. Every second that passes exposes the ship, its systems, and its people to more of these invisible bullets. For the crew, this background becomes their reality. It is not a crisis, it is culture. You can't solve a problem this big just by hiding from it. It's not like running from a storm on Earth. Storms are temporary. Galactic cosmic rays are permanent. They're not weather, they're climate. They surround the ship on all sides, always, in every direction. The further you go from Earth, the worse this climate becomes. And then, there are the solar storms. These are abrupt surges of particles hurled outward by the sun. They are called solar particle events. Unlike galactic cosmic rays, which are a constant background, solar storms happen in sudden, massive spikes. A radiation spike like that can kill, and it doesn't give much warning. When it hits the ship, the crew must be ready. To survive, the ship must include dense, heavily shielded areas where people can hide until the storm passes. NASA's guidelines suggest at least 15 to 20 centimeters of shielding for these refuge areas. That's around 6 to 8 inches. And remember, this isn't foam or plastic, it's dense material that adds enormous weight. For short trips, you can design a small shelter, but for a massive multi-generational habitat, where the mission might stretch over centuries, this shelter isn't furniture you can add to the corner of the ship. It becomes part of the ship's entire structure. Here's where the design shatters. Even when you add the shielding, you don't stop radiation entirely. When a high-energy particle hits shielding that thick, it doesn't stop harmlessly. It interacts. It creates secondary radiation. A cascade of lower-energy particles emerges, sprayed out from the original collision. You aren't just blocking harmful rays, you're creating new ones. This is the reality of shielding physics. It changes the challenge, it never erases it. And it's not just about physics, it's about biology. Radiation attacks life in ways most people can't see. It tears through DNA strands. It mutates cells. It creates stress that the body never evolved to handle. Over days or weeks, radiation can cause immediate sickness. Over years, it's even worse. Tumours, organ damage, degenerating tissues. And these aren't just risks you monitor in adults. This risk impacts reproduction. It places stress on every developing child. What would life be like for generations born into this storm? We don't know, because no life on Earth has ever experienced it. What makes this all so devastating is just how ordinary it looks. 1.5 millisieverts per day doesn't sound dramatic. It sounds like an abstract number, but that small number accumulates quietly without announcement or catastrophe. It creeps into every system. It becomes normal in the worst way possible. Civilization on a generation ship wouldn't fear radiation as an emergency. Instead, radiation would disguise itself as reality, a reality that slowly erodes what you thought was impossible to lose. A generation ship is not just fighting radiation, it's living with it, letting it into every part of the mission, every day, because it has no choice. When we picture a ship travelling between stars, we want to imagine an adventure, a triumph. But the truth is this. A generation ship is less like a triumph and more like a slow-motion radiation accident, one that never stops collecting casualties. When people think of space travel, they think of innovation. They think of lava solutions to impossible problems. Shielding is one of those problems. At first, it seems simple. You just add more layers, more protection, wrap the ship like a bunker and call it good. But deep space doesn't work like that. Shielding isn't just a layer, it's a weight. And in space, weight is destiny. A generation ship needs shielding everywhere. Not just around one laboratory, not just in one small shelter, has to surround the entire living space. That includes walls, ceilings, floors, corridors, and cargo holds. People need protection everywhere. Every part of the ship where someone sleeps, eats, works, or travels has to be shielded. These aren't just small targets like satellites. A generation ship is massive. It has to house hundreds or thousands of people. It needs space for agriculture, storage, life support, and everything else a civilization requires. That means shielding scales up fast. It starts with modest-sounding numbers. NASA's guidelines for long-term space travel suggest you'll need at least 10 to 20 centimeters of water-equivalent shielding in areas where passengers spend a lot of time. Think about that. 10 to 20 centimeters. At first, that doesn't sound ridiculous. It's about 4 to 8 inches thick, depending on the material used. But now imagine covering every wall, every ceiling, every hallway with that thickness. Suddenly, it's not just a shield. It defines the entire design of the ship. The mass goes from manageable to impossible at an exponential rate. The heart of this problem is geometry. Surface area grows faster than you expect. As the habitat gets larger to accommodate human lives, all the walls and structures increase in size too. You can't just think in one dimension. A small capsule might be able to brute force this problem, but a generation ship isn't small. It's a community. Its life support city keeps growing, and with every inch, the surface that needs protection gets larger. That extra shielding means more mass. More mass means more propulsion. More propulsion means even more structure, fuel, and energy. The ship snowballs into something you can't possibly launch. There's another trick people love to imagine. Science fiction even calls it elegant. Use water as your shield, they say, or food or fuel, the resources you're already carrying. And theoretically, this makes sense. Even real mission studies agree this is smart. But the theory ignores what living on a ship feels like. In a generation ship, these resources aren't static. Water moves, food gets eaten, waste gets processed and reprocessed. Storage tanks leak or get repurposed. That water or fuel you're counting on isn't always going to stay in place. It's constantly being consumed or moved. Your shielding is now dynamic. It prevents you from fully reusing spaces or rerouting systems. It's not just protection anymore, it's logistics. And logistics on a generation ship never stay simple. Here's where the problem shifts from physics into something darker. In any complex ship design, some areas will inevitably have more protection than others. You'll build storm shelters to take the brunt of a solar event. These areas will have denser shielding. And because protection is expensive, other areas will have less. So now you've built a hierarchy into the ship. A literal blueprint of privilege and danger. Some spaces are safer, some spaces are not. Generations grow up knowing which compartments are better, which ones people cling to when solar particles slam into the ship. Radiation ends up shaping life on board. It creates social classes built into the walls around them. And here's the thing, the mass needed for these heavy shields doesn't just exist in a vacuum, it has consequences. Adding kilograms isn't free. Every single kilogram in space needs to be accounted for. It has to be launched, accelerated, carried and supported. Every extra kilogram adds strain to propulsion systems. It increases wear and tear. It creates heat that needs to be managed and parts that need to be inspected. The mass of your shielding spreads its burden to every other system on board. The ship has no choice but to become completely interdependent. Even repairs get harder. If something breaks, the shielding itself becomes an obstacle. You can't just remove part of the wall without compromising safety. Inspecting and maintaining such a massive structure becomes a full-time job. The very system keeping people alive makes mechanical failures more complex. In deep space, you quickly realize there are no quick fixes. Every solution introduces a new layer of problems. Now imagine how all this redesign warps the mission. The ship isn't just a transport anymore. It's evolving into something else, something enormous, something planetary. To survive deep space, you don't just need a spacecraft. You need a synthetic ecosystem, a self-contained layered bunker that acts as its own world. This isn't just bigger spaceship thinking, it's planet engineering, but without the natural balance of a planet. And planets are messy, hard to manage, resources flow unevenly, power gets consumed everywhere. Nothing is passive, everything is interconnected. A radiation-proof generation ship looks less like an inspiring dream and more like a juggling act with too many balls. It isn't solving problems, it's postponing impossible choices. Shielding is only one piece of this equation. A generation ship's weight doesn't exist in isolation. Every system on board must work together. Add more shielding and the ship gets heavier. Make it heavier and it needs more propulsion. Create more propulsion and you need more structural support. Build more structure and you need more maintenance, energy and cooling. Every change ripples across every other part of the vessel. And soon enough you're trapped in a feedback loop of escalation. The ship's core design becomes a constant compromise. This is where the concept breaks loudly. A dream of space travel becomes a physics problem that can't be ignored. A generation ship stops being about ingenuity and starts being about entropy. Its systems weigh themselves down over time. Nothing can run forever under these conditions. The shielding mass isn't just a technical issue. It's what transforms the ship into something no one can launch, no one can maintain, and eventually no one can escape. Even if you solved radiation tomorrow, you'd still have another problem. A problem so basic it feels invisible. Gravity, or more specifically, the lack of it. Your body has spent all of human history evolving to live under 1G. That pull shapes everything. Your bones, your muscles, your blood pressure, and how your organs sit inside you. Gravity is not optional, it's part of how you stay alive. So when you take it away, things start breaking down, quickly. In microgravity, the body doesn't sense weight. Your bones stop carrying a load, your muscles stop feeling resistance, your cardiovascular system loosens because blood doesn't pool in your legs anymore. You feel lighter, but your body isn't celebrating, it's adapting. And its adaptation is the wrong answer. NASA has already measured this. astronauts on the International Space Station experience serious changes. In just 4 to 6 months, they lose 1% to 1.5% of bone density per month. Imagine that. Every month, the skeleton gets thinner and weaker. That's about 10 times faster than bone loss on Earth for someone with osteoporosis. It's not just a small inconvenience, it's a countdown to fragility. And muscles, they shrink too. In microgravity, every step becomes easier because there's no real down. Move your leg and it floats effortlessly. Push yourself forward and there's no need to fight resistance. But this ease comes at a cost. Without constant strain on muscles, they atrophy. Within weeks, people lose strength. The longer they're in space, the more it happens. You can fight this with exercise. Treadmills, resistance bands, cycling machines. NASA builds these into every long mission. But exercise in space is not fun. It's mandatory. It takes hours every day. You're not building your body. You're just trying to hold on to what's already there. Think about that. On a generation ship, your crew can sacrifice hours of physical labor each day to stay healthy, or they can lose that health altogether. Either way, the system is paying a price. That's not the only change. Zero-G makes fluids shift inside the body. On Earth, they settle downward. In space, they don't. They float. That's why astronauts' faces and necks swell. There's no gravity pulling blood away from the head, so it ends up pooling there. Long term, this can press on the optic nerve and impair vision. It can also wreak havoc on circulation and cause pressure changes throughout the body. These shifts seem manageable for short trips, but for permanent habitation, it's hard to predict how much damage these changes would stack up over generations. Here's the bigger nightmare. On Earth, crews always recover later. They come back to gravity, their bodies heal, but on a generation ship there is no coming back, no later. No outside world where your skeleton can rebuild itself. The ship is the only home, and Zero-G isn't temporary, it's forever. Some people say countermeasures can fix this. Treadmills, medication and monitoring can keep the crew stable, and they help to a degree, but these countermeasures are fragile. Equipment needs power. Power needs maintenance. Supplies run out. And enforcement, it relies on culture and discipline. Everyone has to stick to schedules and protocols flawlessly forever. Even one generation of complacency could erase progress made by the last. That's not a challenge of technology, that's continuity. And culture is fragile in isolated systems. In space, every forgotten habit, every shortcut, every small lapse can compound. The treadmill in year 5 may still be running. But will the treadmill in year 85, 185, maintenance becomes culture? Culture becomes survival. If you lose that, you lose the mission. It's also critical to realize that countermeasures aren't solving the problem. They're just masking it. The ship is treating symptoms, not creating a natural fix. Because here's the real issue. Microgravity actively works against you. It's not passive, it constantly undermines every system meant to keep the crew alive. Zero-G isn't just no weight, it's an invisible attack. It attacks your physiology, making bones weak and muscles useless. It attacks morale, draining time and labour. It even attacks your future, because you can't plan generations of health around systems designed for temporary resilience. And no system exists perfectly in isolation. Without gravity, every other system on board has to take on more burden. Weak bones and atrophied muscles mean the crew becomes physically fragile. Fragility means extra stress during emergencies. Medical systems have to work harder when common accidents turn into life-threatening problems. Think about fractures, rare on Earth, catastrophic on a ship where bones are already compromised. Weak, unstable bodies also strain social roles. Repairs, maintenance, farming, and even survival tasks get harder. Someone has to keep scraping whole panels or fixing circuits, and fitness programs or medical care won't create more muscle mass out of thin air. Decades of weakened labour become the new standard. No amount of encouragement changes the limits of what fragile bodies can do. Without gravity, normal life doesn't exist. This isn't part of the sci-fi fantasy, the artificial calm you see in movies. It's not just a quirky environment where tools float. and hair sticks up. It's a gravitational condition that forces the entire mission into a state of dependency. Everything you knew about human durability on Earth starts to disappear. So what can you do? Some people believe artificial gravity can solve everything. Just spin the ship, they say, generate force by rotating it around an axis, and suddenly you have weight again. Floors feel like floors. Bones and muscles have pressure again. But solving one issue just opens up new disasters, because building a rotating ship is engineering chaos. Here's the brutal takeaway. Without gravity, both the crew and the mission fall apart. Slowly, steadily. And even if gravity is artificially recreated, the design sacrifices that follow might break the ship in new ways. A generation ship can handle weightlessness for a few months, a few years, but not forever. Microgravity isn't just a background condition, it's hostile. And when combined with every other challenge, it becomes another reason this concept isn't just difficult, it's impossible. So you spin the ship. Problem solved, right? You get gravity back, the body stays healthy, bones stay strong, muscles work like they're supposed to. Everyone walks normally. It sounds simple, but the reality is nothing like the fantasy. Artificial gravity isn't magic, it's real physics. And physics? It plays by brutal rules. To make artificial gravity, the ship has to spin. The faster it spins, the stronger the gravity. And the larger the radius of the spin, the smoother it feels. You can calculate how much force you get based on the speed and size of the rotation. The problem? That calculation doesn't care what's easy to build. It demands a design that quickly becomes unrecognizable. For a ship to create 1G, Earth gravity, with a comfortable spin, NASA estimates it would need a radius of about 35 meters if you were spinning at 5 rotations per minute, RPM. That's roughly 115 feet. Is that big? Yes, but it's doable. But what if you want to make the radius smaller? Say around 4 meters or 13 feet? Then you'd need to spin the ship at 15 RPM to generate the same 1G. The math works fine. The humans inside? Not so much. Spin faster and problems with motion sickness explode. At high RPM, your body feels forces it has never evolved to handle. Even worse, at small radii, say under 10 meters, your body won't feel gravity as a smooth, even force. Gravity won't feel like it does on Earth. Instead, your head and your feet experience completely different forces. Imagine standing in a room where your feet feel heavy, but your head feels light. That's what happens in small radius centrifuges. Your body is being stretched across competing forces. This difference in forces is called a gravity gradient. NASA's experiments show that in small areas, the difference across the body can go from 20% to even 100%. So you're standing, but your body is experiencing something unnatural, something it didn't evolve for before. Your legs feel one weight, your torso feels another. Your brain, meanwhile, tries to make sense of it all and struggles. And moving inside a spinning habitat doesn't feel normal either. The moment you turn your head quickly or walk forward or stretch, your body feels forces that don't exist in Earth biology. These effects come from Coriolis forces, and they don't just make things uncomfortable, they drain you. Every small movement takes more effort to adjust to. Looking around, it can make you dizzy. Turning too fast, it can make you nauseous. Artificial gravity fights one problem by creating a whole new set of problems for basic movement. Astronauts and test subjects have tried to tolerate this before. Studies have been done in centrifuges, where people train under different spin rates. Russian experiments in 10-meter radius centrifuges showed that people could handle 12 revolutions per minute after just a few days. Some longer tests went to 25 days at 6 revolutions per minute. And yes, those people adapted. But adaptation wasn't smooth. It came with motion sickness, headaches, coordination issues, and fatigue. For 25 days, those symptoms seem manageable. But this isn't a training session. A generation ship would spin for centuries. And no short experiment can really tell us what those dizzying effects would do to the human body or human culture in the long term. And if that sounds difficult, remember, spinning the ship isn't just about the people inside it. The ship itself has to handle the forces. A rotating megastructure comes with a whole suite of unforeseen design problems. Bearings and seals aren't built for eternity. These massive spinning components wear down over time. Maintenance becomes harder because every joint, surface, and connection is under physical stress. And when you need to repair something critical, you're repairing it in motion, inside a geometry that's constantly twisting with centripetal forces. Docking is also harder. Imagine a small pressurized craft trying to meet up with a giant rotating ship, a moving target, and even plumbing becomes more complicated. Fluids don't simply flow in straight pipes anymore. Wastewater, air, oxygen, all need to work inside a structure where up and down depend on how close you are to the ship's center. Every system on board would need to be re-engineered for these unique conditions, creating cascading points of failure that no traditional spacecraft faces. None of this is cheap or elegant. It's like solving one problem by introducing 5 new ones. You solve bone degeneration, but you create chronic motion sickness. You solve muscle atrophy, but you make maintenance far more dangerous. The spinning creates gravity, yes, but at the cost of reliability. Even building the rotating structure in the first place is a gauntlet of near impossible challenges. The ship has to be lightweight enough to launch, but hardened enough to spin and survive under constant environmental stress for centuries. Every bearing, every structural beam, every load path has to tolerate forces pulling in all directions for an unimaginable span of time, all while being subjected to micrometeoroids, wear, and material aging. And the larger the radius, the more mass you'll need just to keep the structure from ripping itself apart. But if the radius becomes too small, adaptation for the crew becomes unbearable. It is a balancing act where both options, small or big, are deeply flawed. The promise of artificial gravity seems so clean in science fiction. It is the cinematic reset button. Weightlessness hurts the mission. Spin the ship. Mission saved, but the reality is so much more complicated. Creating artificial gravity doesn't fix the ship. It alters the ship. It turns it into something harder to maintain, harder to survive in, and far more fragile. Deep space is relentless. No gravity is deadly. Artificial gravity is a nightmare of engineering compromises. There's no clean way out of this. Choose 0G, and you wear the human body down over time. Choose spin, and you add impossible layers of structural and operational risk. This is the hard truth. Artificial gravity isn't just a solution. It comes at the price of building an entirely different kind of ship. One that's more like a rotating nightmare of centrifuges and complexity. The fix quickly becomes its own trap. Artificial gravity transforms the ship from a hopeful journey into another delicate system of compromises. Gravity stops being a win. It becomes an endless engineering tax. You can measure oxygen. You can calculate how much the crew needs to breathe. You can run equations to figure out carbon dioxide levels. Numbers seem manageable. They give you a sense of control. But life support isn't just about numbers, it's about biology. And biology doesn't care about your plans. That's what makes closed-air systems so dangerous. Because they don't behave like machines, where every input matches a reliable output. They behave like ecosystem, complex, chaotic, and unpredictable. A generation ship has no outside air, no wind, no fresh supply of oxygen from plants in forests or oceans. The air has to recycle perfectly forever. And if it doesn't, people die. We've actually tried something close to this on Earth. Biosphere 2 in Arizona. It wasn't a spaceship, but it was the closest thing humans had built to one. A sealed habitat about 3.1 acres large. A crew of 8 people tried to live there for 2 years, relying on recycled air, water, and food. Everything was self-contained. It was supposed to prove we could engineer closed systems for survival. Instead, it proved how easily those systems break down. The oxygen in Biosphere 2 dropped to dangerous levels. Carbon dioxide surged. The system looked functional. Nothing had exploded, nothing was visibly wrong. Yet the air became unbreathable. Crops struggled. The crew's energy and cognitive performance slipped. And here's the terrifying part. The habitat was still standing. It still looked fine. No alarms went off, no dramatic failures. Why did it break? It wasn't one big mistake. It was small things, invisible things. The soil was alive. Microbes in the dirt were consuming oxygen. They were releasing carbon dioxide faster than expected. At the same time, the concrete inside the habitat was reacting with carbon dioxide chemically, absorbing it into the walls. These interactions weren't part of the plan. The container itself, the building, the materials, the ecosystems inside, became active parts of the experiment. That's the nightmare of a closed system. It's not just a can you live inside, it's alive. The walls, the dirt, the air, everything interacts. Everything has feedback loops. And those loops don't always stabilize, they can drift. Carbon dioxide doesn't even have to rise to insane levels to start hurting you. Inside Biosphere 2, carbon dioxide levels climbed high enough to impair thinking and performance. Meanwhile, oxygen dropped. At one point, it fell to levels you'd experience 17,000 feet above sea level. That's around 5,200 meters. It's like living in the mountains with no option to go lower. Your thinking slows, your memory suffers, you feel tired and ineffective, and you may not even notice it's happening at first. The air is still there, but it's no longer doing its job. How did they save Biosphere 2? Not elegance, not engineering brilliance. They saved it with tank trucks. After a year and 4 months, they brought in oxygen from the outside. Roughly 31,000 pounds, about 14,000 kilograms. They had no choice. Without those deliveries, the experiment would have endangered the crew. And think about that for a second. Biosphere 2 wasn't cut off. It wasn't flying through deep space. It was sitting on Earth. It had access to engineers, scientists, resources, and help. And even then, it needed tank trucks full of oxygen to keep it going. A generation ship doesn't get tank trucks. There's no delivery service crossing interstellar space. There's no one to call for help. The habitat has to work perfectly, without external input for generations. Biosphere 2 lasted about 16 months before running into serious chemical imbalances. A generation ship would have to run for centuries without crashing even once. Some people think plants will save the mission. The plants will photosynthesize, converting carbon dioxide into oxygen. They'll create the perfect balance. But plants aren't machines. They don't flip a chemical switch and obey humans. They're living organisms with their own needs, their own rhythms. They also breathe through a process called respiration. At night, or when light conditions change, they consume oxygen instead of producing it. Plant productivity also depends on so many factors: light, nutrients, disease, crowding, stress, temperature, even the state of the microbes in their soil. The very complexity that makes plants valuable also makes their efficiency unpredictable. They don't work like pipes or filters. They work like ecosystems, messy, variable, non-linear. Managing air with plants isn't just set it and forget it, it's an active process. It means balancing crops with conditions, fixing the nutrient cycle, controlling light schedules, protecting plants from disease, and still, systems drift. That drift can sneak up on you. No warning lights, no big failures, just small changes in how the air feels. Maybe people start sleeping worse, maybe they feel more stress, maybe they make more mistakes. Over time, these small effects compound. The very people running the life support systems are the ones impacted by those systems slowly slipping out of balance. It creates a feedback loop. You end up with a ship where survival looks normal until it doesn't. There are no dramatic hull breaches or catastrophic events, just air that makes you slower, weaker, and less effective. Just systems that seem functional, but no longer support life the way they're supposed to. At some point, the crew won't notice the exact moment things went wrong. They'll just exist in a state of constant struggle, compensating for systems that feel slightly off but never truly recover. The ship isn't just a closed environment anymore. It becomes a civilization, trapped inside its own failing metabolism. And here's the critical part. No amount of future tech could erase the chaos of closed systems. The air is the ship. The feedback loops are inevitable. And the longer the mission stretches, the less breathable it all becomes. When people hear about water recycling in space, they think we've already solved it. The ISS recycles water all the time. It reclaims urine, sweat, and even humidity from the air. Sounds impressive, right? And it is, on Earth's scale. But the ISS isn't a generation ship. The ISS has constant support from Earth. New filters can arrive, spare parts ship up, crews go home. None of that exists on a generation ship. Water recycling doesn't just have to work, it has to work forever. No resupply, no fresh filters, no backup support. It has to sustain every single person on board through recycling that never drifts out of balance. And that kind of perfection doesn't exist. Not in human engineering, not in human history. Here's what people misunderstand. A water recycling system is chemistry, not magic. It relies on filters, membranes, catalysts, and storage containers, all of which degrade over time. Every system loop has surfaces that wear down. Pipes can erode, filters clog, pumps malfunction, and microbial risks grow. All of this happens in space where replacements are non-existent. Even the tiniest problem can spiral. In an open system, contaminants disappear into infinite reservoirs, like a river or a sewage plant. But close the loop and nothing escapes. Trace chemicals accumulate, invisible contaminants compound. Eventually, water that looks safe may poison the people drinking it over months or years. Deep space never forgives build-up, and the numbers already show how much water a generation ship would need, even under ideal conditions. A closed-loop design from the Melissa program, one of the most advanced space life support studies, targets around 15.8 kilograms of water per person per day. That's about 35 pounds of water per day per person. That includes drinking, food needs, oxygen recovery, and waste management. These targets aren't just numbers, they're warnings. Multiply them by the population of a generation ship and you're dealing with an industrial-scale recycling plant. Not a small machine, not something manageable. It's an economy-sized problem masquerading as a life support system. And yet there's something even scarier hiding inside water loops. Biofilms. Microbes. The moment you start recycling water, you create an environment microbes love. Water systems are wet, warm, nutrient-rich, and full of surfaces, exactly what bacteria want. Microbial colonies stick to pipes, clog membranes, and form films that are almost impossible to fully clean. This isn't hypothetical. It happens even in well-monitored systems. On Earth, we deal with it using aggressive cleaning methods. We shock pipes with chemicals, we overflush systems, we replace problem areas. But on a generation ship, every extreme cleaning action risks collateral damage. Tip too far into sterility, and you might hurt the crew or disrupt the system's delicate loops. But allow microbes to thrive and they can take over. Sterility and ecology clash in closed systems. It's an endless balancing act. And every time something fails, it's not just an inconvenience. It's a public health event. A single failed seal isn't just a mechanical error, it's contamination. Bacteria can spread into drinking water, or chemicals from a broken filter can hit toxic levels. And when systems are this interconnected, a problem in the water loop doesn't stay there. It can spread into the food chain, the health system, even into medical care. Water isn't just plumbing on a generation ship, it's tied to every part of life on board. Miss a filter change and you don't just skip maintenance. You risk exposure to microbes or chemicals that could make the crew sick. Every seemingly simple act of neglect, whether caused by failure, mismanagement, or even accidents, has the power to cascade. The pipes aren't just pipes. They carry health, safety, and morale through every part of the ship. And worse still, the ship itself is fighting against you. Pipes age, materials corrode, microbes evolve, filters and membranes degrade. Water may stay liquid, but reliability doesn't. Systems that work well for a few years don't translate to systems that can run for centuries. There is no water tech today, or even on the horizon, that we know will perform flawlessly under a timeline this long. That's the core problem with water recycling aboard a generation ship. Time. Even if you build a water loop that works, and some designs are impressive, it's nearly impossible to guarantee it stays chemically balanced, clean, and safe for hundreds of years. Human industrial civilizations don't have a single closed utility system that's lasted this long, not one. And those are systems on Earth with full access to resources and expertise. Now imagine doing it in the vacuum of space, with no backups, no spare parts factories, no experts arriving to check your work. This is where the theory of water recycling meets reality. It's not just keeping liquid moving through pipes, it's full recycling, full maintenance, full sterilization, full chemical safety, all without failure. And it's not just one ship that has to succeed, it's an entire civilization on board. Generations of people must rely on this delicate water cycle without ever sliding into chaos. The numbers don't lie. Water needs are enormous. Filter and treatment surfaces degrade. Microbial biofilms evolve into hard enemies, and every failure becomes a public, social, and technological disaster. A generation ship may carry liquid water, but when you look deeper, the loop keeping it clean can never stay as perfect as theory demands. That's the mismatch that crushes every dream of long-term water recycling. It's not just engineering, it's an impossible battle with time. Food doesn't seem like the hardest part of a space mission. People picture astronauts eating vacuum-sealed pouches and pre-packaged meals. Seems straightforward. Pack enough food before launch, ration it carefully, and that's it, right? But that's not the reality. Not for a generation ship. Because food is never just food. It's life support, it's culture, it's chemistry, and it's endlessly complicated. The first problem: calories aren't abstract, calories are real. They take space, they take weight. NASA's research on space food shows the limitations clearly. Stored foods degrade, they lose nutrients over time, vitamins like B1 and C don't last forever. Even the best storage techniques today can keep food shelf-stable for 3 years at most before some parts of it start to break down. But a generation ship isn't just running for 3 years, it's running for decades, for centuries. You can't load a ship with enough food to last that long. It's not a matter of how big your pantry is. It's about chemistry and biology. Food stored over too much time either rots, loses nutrients, or deteriorates in taste and quality to the point where it becomes a health or morale risk. So storing food solves one problem: launch. You get the ship off the ground, fully loaded, but stored food doesn't solve the voyage. Eventually, no matter how well packed or insulated, those supplies will run out, and people can't stop eating. Food isn't optional inventory. Every single day the crew consumes energy. They replenish their bodies by processing nutrients into life itself. Unlike spare parts or tools, food isn't something you can ration once and forget. It has to renew constantly. The ship doesn't just sustain the people on board, it must actively produce what they eat to survive. That means agriculture. And agriculture on board a generation ship is less like gardening and more like industrial science. You can't just plant a few crops in some dirt. Controlled environment agriculture is the only option. Growing food in sealed habitats with recycled water, artificial light, precise nutrient dosing, and complete pest control. We've tried systems like this on Earth. The Eden ISS project, a greenhouse analogue in Antarctica, produced about 268 kilograms of edible biomass from a small 12.5 square metre area. That's around 591 pounds of food from 135 square feet. If that seems like a lot, remember, it's just a highly controlled science experiment. They carefully managed every variable, like light intensity, temperature, water use, and nutrient levels. In space, you'd have to replicate those conditions in even more extreme circumstances. You wouldn't just be growing lettuce in a greenhouse, you'd be running an industrial-scale agricultural factory for generations. Even then, most of what grows well in these environments isn't everything people need to survive. The Eden ESS trials leaned heavily on fast-growing, nutrient-dense plants like cucumbers, lettuce, leafy greens, and tomatoes. All great for vitamins, all great for morale, but they aren't enough to feed a human body completely. Sustaining people over decades or centuries requires staples. You need carbohydrates, proteins, and fats in large, balanced quantities. You need grains, legumes, and calorie-dense crops, things that aren't as easy to grow in controlled conditions. Every calorie produced, every essential nutrient provided, comes at a cost. The ship doesn't have sunlight the way Earth does. Plants depend on light to grow, to photosynthesize, to turn energy into food. On Earth, that energy comes free from the sun. On a generation ship, it doesn't. You're paying for every photon with artificial lamps. You're paying for heating and cooling to keep crops at the right temperature. You're paying for humidity control so the air around the plants doesn't oversaturate. And water, endlessly recycling through the system, has to be precisely dosed with nutrients, neither too weak nor too strong. Every single step costs energy. And it gets worse. Plants aren't independent systems. You're not just growing leaves, you're growing ecosystems. You need to schedule crop rotations to keep soil or substrate productive. You need to account for plant diseases, fungal risks, and pest management. Even under controlled conditions, plants live and die inside feedback loops, and managing those loops takes constant attention. Constant resources. Farming as we know it collapses into something unrecognizable, a machine-driven imitation of Earth's natural balance. But here's the problem that will break every plan. People don't survive on calories alone. A generation ship isn't just trying to meet biological needs, it's trying to meet cultural and social needs. And food is a huge part of human life. It's not just sustenance, it's identity, it's tradition, it's morale. Imagine living your entire life eating nothing but calorie slurries, vitamin-enriched pastes, and occasional bland greens. Imagine raising children on a ship where every meal feels the same, where food is stripped of joy and identity. For a short mission, people could tolerate it. For a voyage that stretches over centuries. It's a recipe for psychological collapse. Food must be nutritious, but it must also be fulfilling. It has to taste good. It has to break monotony. It has to offer variety. People don't just eat to survive. They eat to enjoy, to connect, to celebrate, and to create. Food is culture, and culture keeps civilization from unraveling. This creates a new dilemma. You're not just trying to grow lettuce, you're trying to grow cuisine. You're not just rationing calories. You're designing a system that balances energy costs, environmental loops, psychological needs, and human traditions. And all of this depends on the crew liking what they eat. That might sound trivial, until it isn't. A crew that hates their diet grows resentful, hostility brews, monotony sets in, and you can't just fix it later. Once food feels like survival drudgery, the ship's society suffers with every meal. This psychological toll ripples outward, creating hidden fractures in morale and trust. What starts as calories becomes identity. What starts as farming becomes social stability. Food reveals the real problem. A generation ship isn't a closed spaceship. It's a counterfeit biosphere, trying to cram the complexity of an entire planet into a sealed artificial container. And nowhere is this challenge more obvious than in food production. When people imagine a generation ship, they think about its passengers, the humans, their children, their descendants. But a generation ship doesn't just carry people, it carries everything that comes with them. Skin bacteria, gut microbes, viruses, fungi, food-related organisms, the hidden, invisible ecosystem that every human body needs and can never fully control. This isn't a small detail. It's a problem so fundamental that it reshapes the mission. People assume a sealed ship is clean, that once it's launched, no new diseases can enter, that the crew is safe. But that's not how biology works. The danger on a generation ship isn't from the outside, it's from what you bring with you. The microbial world doesn't stay static. It evolves, it spreads, it turns the ship into what it always was, a massive experiment in closed system biology. The first mistake people make is thinking isolation means safety. It doesn't. Humans don't exist in sterile conditions. Every breath they take, every surface they touch, every meal they eat adds microbes to the environment. Isolation doesn't stop that. It concentrates it. Every ounce of the ship's air, water, and surface areas becomes a shared reservoir. Pathogens have nowhere to escape. People have nowhere to escape either. Infected water? It circulates. A cough in one compartment? It spreads to another. On Earth, diseases sometimes fizzle out because networks break. People stay distant. Resources buffer outbreaks. On a ship, those barriers don't exist. Air is recycled, surfaces are reused, and diseases don't even need to come from the outside. Some of the worst threats might already be on board. Why? Immune systems in space don't act normal. Research from spaceflight missions shows something chilling: immune dysregulation. Astronauts show reduced immunity to infections after months in space. Stress, radiation, and microgravity push immune systems into fragile, sluggish states. Your defenses weaken. What's worse, viral reactivation. Dormant viruses, ones your body has otherwise kept in check, can wake up under these conditions. Herpes viruses, for instance, have a known history of re-emerging during extended missions. On a generation ship, this is catastrophic. Think about it. Every passenger brings their own immune history into the mission. They might look perfectly healthy at launch, but carry dormant viruses like time bombs. Stress builds, immune defenses weaken, viruses activate. Suddenly what seemed contained isn't anymore. These aren't new passengers causing problems. These are infections rising from inside your own crew. Microbes evolve as well, and they do it fast. A generation ship systems would rely on stability, stable medicine, stable ecology, stable procedures. But microbes don't care about stability. They mutate. They compete among themselves. They adapt to exploit tiny failures in their environment. And the ship is full of surfaces, fluids, and systems that give them opportunities. There's evidence that even under spaceflight conditions, some bacteria express increased virulence or higher resistance to antibiotics. Couple that with a closed habitat on a scale this large, and your medical system isn't fighting yesterday's pathogens, it's fighting a moving target. The library of threats grows and changes. The ship has no access to external supply chains. No sudden resupply of drugs or treatments. The ship's medicine has to handle every microbial surprise without failing once over centuries. It's impossible. The environment doesn't just attack humans, it attacks the ship itself. Microbes colonize water system, pipes and waste processors. They clog filters, they grow biofilms inside nutrient loops. A small outbreak in one system spreads into others. Suddenly, what started as a microbial problem becomes an engineering problem. A filtration issue becomes a food production issue. A food issue creates morale and health problems. This is cascading failure. One weak spot infecting everything else. You're dealing with a paradox. The ship needs to stay biologically active. It needs microbes to function for waste recycling, plant growth, and closed-loop systems. Without microbes, life support collapses. But with too much microbial growth, the ship mutates into a health hazard. Balancing this isn't just hard, it's contradictory. High biological richness and high medical sterility are at war with each other, and the ship needs both to survive. Imagine this. You're trying to maintain a permanent hospital inside a permanent petri dish. That's what a generation ship really is. The passengers depend on medicine to keep them healthy. On Earth, hospitals have technology, staff and support networks to handle outbreaks. Ship has none of that redundancy. There's no CDC stepping in. No off-site lab to analyze new pathogens. The people on board must remain healthy while also keeping the bioreactor systems alive. And the longer the mission stretches, the worse it gets. Every new generation inherits a microbial habitat that isn't the one they left. Bacteria mutate, systems age, medical supplies dwindle. At first, life on board might look manageable. But small failures compound. A clog in a pipe becomes widespread contamination. A minor infection spreads into a shipwide crisis. The hard part, these aren't flashy cinematic failures. There's no alien invasion or dramatic disaster. Just small invisible mismatches in biology. Bacteria evolving faster than you can respond. Viruses reactivating in stressed, exhausted passengers. contaminants creeping into water systems, recycling endlessly, and behind it all, a society of people trying to contain a situation they cannot fully control. A sealed ship isn't safer, it's riskier. Every microbial threat that boards the ship stays there, and every fight against it is a fight against time, over decades, over centuries. The ship and its ecology will never stop trying to drift out of balance, and the passengers will never stop paying the price. Deep space looks empty. It feels vast, silent, and open. That's the comforting illusion. But the truth is, deep space isn't empty at all. It's filled with things, tiny things moving unimaginably fast. Invisible gas, specks of dust, and grains of debris are scattered everywhere. Even in the interstellar void, these materials exist. Rarely enough that it seems empty at first glance, but over large distances, they add up. The longer the journey, the harder it is to avoid them. This is a problem you cannot see, but it can destroy a spacecraft just the same. NASA's calculations revise the interstellar medium to about 0.127 hydrogen atoms per cubic centimetre. Imagine a quart, and imagine about 120 atoms floating invisibly inside it. That doesn't sound like much, but over interstellar distances measured in light years, not miles, it stops being nothing. And particles of dust, even more dangerous. Voyager mission data proves that interstellar origin grains constantly impact travelling spacecraft. Some of these particles are moving at speeds of 26 kilometers per second. That's 58,000 miles per hour. Faster than anything in your daily life. Faster than anything we experience on Earth. And here's what makes this terrifying. When objects collide at hypervelocity, their energy doesn't scale normally. Kinetic energy increases with the square of the velocity. That means a tiny particle barely visible can strike with the force of a bullet, or worse. One tiny grain becomes a projectile. 1,000 grains become deadly sandpaper. Spread over interstellar travel distances, this sandpaper turns the vacuum of space into something more like a storm. Your ship isn't quietly gliding through emptiness. It's weathering a constant high-speed drizzle of destruction. This kind of danger changes how we think about damage. On Earth, a speck of dust is harmless. It falls to the ground, you wipe it off, it doesn't matter. But at tens of kilometers per second, a grain of dust isn't harmless. It penetrates. It embeds itself into surfaces. It breaks apart on impact, releasing energy into the material it hits. Erosion becomes meaningful. The question for a generation ship isn't whether these impacts happen, it's how long the ship can survive before the damage overwhelms it. We already know that even near Earth, impacts add up. The International Space Station ISS is protected in low Earth orbit, yet it collects damage constantly. The ISS requires hundreds of shields to protect against micrometeoroids and orbital debris. Shuttle missions reported over 1,500 hypervelocity pits accumulating in windows, and 130 of those pits directly damaged the glass enough to require replacement. That's near Earth, with constant maintenance access. Imagine the same conditions, or worse, on a ship that can't dock, can't replace windows, and can't rotate parts out for repairs. A generation ship doesn't survive this for decades. It must survive it for centuries. And not all parts of the ship are equally vulnerable. Transparent surfaces like windows or sensors are an extreme weak point. Glass and sensor panels on spacecraft develop craters much larger than the actual impacting particles. NASA's studies on hypervelocity damage show that fused silica used in space windows can develop impact craters 30 to 50 times larger than the size of the grain that hit it. Transparent surfaces are under permanent assault. A cinematic image of a giant viewing window on a generation ship? Pure fantasy, it would never last. In reality, your ship has no giant observation bubbles. No romantic views of the stars. It has shutters, layers, redundant panels, and eventually no windows at all. Everything exposed to space must be hidden behind armour, or you lose it. But here's the kicker. Damage isn't just about cracks or punctures, it's about slow decay. Even impacts too small to notice have consequences. Transparent materials don't just crack, they lose clarity. Surfaces become rough. Optical systems become less effective. Hull panels develop microscopic flaws that weaken over time. Solar panels lose efficiency. NASA documented this on its missions. The buildup of tiny impacts led to broken bypass diodes and overheating in solar arrays. Even if meteorites don't rip holes in the hull, the ship becomes weaker, less efficient, and harder to maintain with every passing year. Over a timescale of generations, this erosion becomes relentless. It's not about one dramatic collision. No asteroid slamming through the ship. No chaotic breach. Just millions of small, forgettable impacts, over and over, sanding the ship down bit by bit. Every particle, every grain takes something away from the ship. A bit of strength, a bit of clarity, a bit of efficiency. And now imagine trying to design for this. You can add shielding, but shields add mass. Every kilogram added to a shield must be accelerated, supported, cooled, and structurally anchored. Shields aren't magical force fields. Every solution you apply feeds into other systems. The more weight to your shield, the harder it becomes to propel the ship at all. And shielding isn't invincible. It absorbs impacts, but it also becomes damaged itself. Protective layers wear thin. Replacements aren't easy. A shielded hull must be armoured and maintainable over centuries. The worst part, damage creates cascading effects. A tiny fracture in a hull panel can grow into a structural weakness. A cracked sensor might misread crucial data. A degrading solar array reduces power for life support. One weak point spreads pressure to others. One flaw becomes 10 larger systemic problems that weren't there before. Deep space doesn't need giant collisions to kill a ship. It doesn't need one dramatic event. It just needs time. The ship faces endless sandblasting, courtesy of a medium people insist on calling empty. The hull might survive a year, a decade, a generation. But statistically, it's never really winning. It's just enduring. Micrometeoroids, dust particles, gas ions. None of them stop coming, and the ship never gets a break. A generation ship doesn't just need to be built tough, it needs to be built invincible. And modern space engineering doesn't do invincible. It does replaceable, exchangeable, repairable. None of those options exist once the ship drifts too far from Earth. No spare parts are arriving. No fresh panels are being swapped in. The hull needs to take thousands, maybe millions, of tiny blows over its lifetime, and it has to resist all of them without failure. The real enemy isn't a single impact. It's accumulation. Damage that seems small at first glance adds up, and generation ships aren't built for a peaceful crossing. They're forced to fight an invisible war against their environment, a war they cannot win. Over centuries, the ship and its systems grind down. Little flaws become big ones. Perfect systems become riddled with imperfections, and when they finally break, no one on board will say, "I saw it coming." They'll only see the final consequence of countless tiny blows that no one could stop. Radiation doesn't just attack people, it attacks everything, including the ship's computers. And here's the problem. Computers don't need to die to fail the mission. They only need to misfire, to think wrong, once, at the wrong time. NASA already knows how this happens. They've studied single event effects, or SEEs. When a charged particle hits a semiconductor chip, it can disrupt how that chip works. It can flip a memory bit, turn a 0 into a 1, corrupt a register, or throw the entire system into a bad state. A single particle, invisible to the naked eye, can rewrite vital system logic as if reality itself had glitched. On a short mission, we can manage this. Redundancy helps, backup systems, error-correcting codes, fail-safes. You can reboot, reset, or swap hardware if something glitches. But a generation ship? That's different. You're not asking whether an error will happen, you're asking whether you can survive endless small errors for centuries. That's not engineering anymore. That's gambling. And not every glitch is the same. Some are recoverable. NASA calls these soft errors. A reboot can clear the problem, or the system can correct itself. But some errors are hardware failures. These are hard errors. A latch-up could require a full system power cycle, a burnout can permanently destroy components, or a particle can rupture a transistor gate. Damage like this doesn't fix itself. Once the hardware dies, you're down a system. Permanently. The nightmare of a generation ship isn't one big catastrophic computer failure. It's the stack of smaller failures that accumulate over time. Intermittent glitches, sensors that degrade, small resets that erode confidence, gradual losses that consume spares, and patience. People imagine the ship protected by radiation shielding. Shielding helps, but not enough to erase the problem. See, mitigation isn't one size fits all. Every component needs its own protections. Every system needs error detection and correction. You need redundancy, specific design analysis, careful part selection, and constant testing for how radiation might interfere with operations. There's no such thing as a radiation-proof computer. At best, you get risk reduction, not risk elimination. And a generation ship lives under the worst possible conditions, long-duration missions, no resupply, constant exposure to cosmic radiation, high consequences for failing systems. You're building for probabilities stretched across time, the kind of risk that shatters optimism and leaves you with a deep, fragile uncertainty. Electronics also face another brutal trade. Mature components, older chips, are easier to predict, but they lag in performance. Newer components provide better performance, but are often more sensitive to damage. You can't afford to get the best, you need the tough. But here's the catch. You can't keep refreshing the ship's electronics with Earth's supply chain. No resupply means no upgrades, no repairs from new production stock. Eventually, your generation ship becomes a museum for its own technology. It no longer moves forward. It preserves what still works. Its electronics culture becomes a preservation society, avoiding obsolescence for as long as possible. But the longer the mission, the harder this becomes. At some point, the industrial base that built your components is gone, the expertise fades, and your crew is left maintaining artifacts they didn't create, using tools they can't replace. Here's the truth. A generation ship doesn't need to experience ghosts in the machine for its systems to fail. It's haunted by statistics, by probability, by soft errors that don't kill but interrupt, by weird values that show up in sensors when they shouldn't, by incorrect records in medical systems, one error at a time, by navigation mismatches that make you question whether the ship knows its location. A single reboot doesn't seem like a big deal. A single checksum error seems like a fluke. A weird sensor value doesn't ruin the day. But over a century, over generations, these little glitches add up. They accumulate. The mission only works as long as every system retains enough stability. Every time a bit flips wrong, trust degrades a little more. Confidence in the ship's unseen logic starts to erode. This is the trap of relying on computers for life support, navigation, and control. You're not just asking for reliability, you're asking for perfect reliability forever, with no resupply, no easy replacements, no fresh start. You're playing a game of digital hygiene, where the smallest slip might compromise everything. Think about this. Digital systems need regular maintenance even on Earth. Software updates, hardware replacements, troubleshooting. That happens here with skilled engineers, factories and infrastructure backing it up. On a generation ship, there's no backup, no second supply chain if the first one fails, no emergency delivery of spare chips. The ship becomes its own trapped digital ecosystem, isolated, decaying and at the mercy of time. In deep space, radiation doesn't stop, it keeps bombarding the ship every second. Every circuit aboard is running a slow-motion lottery. No one error is fatal, but errors aren't rare, they're constant. And slowly, they chip away at functionality. A reset may fix today's problem, but what about next year? What about 50 years from now? What about 200? A single error doesn't matter, 100 don't. But 10,000, a million? Generational scale missions are about accumulation, not isolated events. And the ship isn't just carrying people on a voyage, it's carrying their hopes, their survival. all managed by systems that are quietly decaying under the pressure of time. Interstellar radiation doesn't need to destroy the ship's computers. It doesn't need any dramatics. It just needs to keep flipping bits, one particle at a time, until failure is baked into the ship's reality. People think a generation ship is all about endurance, big, majestic, humanity's greatest feat, but the reality isn't glory, it's maintenance. Because in deep space, nothing lasts forever. Not machines, not pipes, not seals, bearings, circuits, or even the walls. Every single part of the ship is trying to fail. The only question is how long the crew can prevent it, and what happens when they can't. NASA already knows how brutal this is. Their studies on ultra-reliable systems for space missions say it outright. Long-duration missions require extremely low failure rates. And here's the key: no resupply. Nothing can break without a plan to fix it. Nothing can wear out that isn't replaceable. Everything has to be maintained. Every time, for generations. Some people think the solution is simple. Just engineer it better. Make systems ultra-reliable, build them tough enough to last. But that's not how the engineering works. The closer you aim for perfection, the harder and more expensive it gets. Testing reliable systems isn't linear time balloons, cost spirals, and the gains become razor thin. You can't just make it better forever. Reliability comes with limits. So if things will break, what's the real answer? Spares, lots and lots of spares. NASA analysis shows this reality clearly. When you build systems, toy-level reliable, they need backups. For deep time survival, the spare mass needed can eventually match the mass of the systems themselves. Imagine what that means. Every critical piece of the ship must have replacements. Every pump, every valve, every fan. The ship starts duplicating itself in storage. Spare parts grow inside the crew space, filling lockers, bulkheads, and cargo bays. Half the ship is just a reserve for when the other half breaks. But it's not just the big systems making this nightmare harder. Small, invisible parts are breaking down constantly too, like lubricants. NASA's tribology studies on liquid lubrication are clear. Lubrication in space becomes a hidden enemy. Lubricants evaporate. They creep away from where they're needed. Bearings wear out faster without them, and starved bearings grind themselves into useless chunks of metal. A generation ship is filled with rotating, moving, sliding equipment. Centrifuges for artificial gravity, pumps for water loops, fans for ventilation, tiny actuators indoors, tools and manufacturing systems. Every one of those parts depends on lubrication, and every one of them is a silent timer ticking down to failure. Replacing a worn-out bearing might seem easy, but do it 100 times, 1,000, over centuries. Suddenly, slick mechanics become a never-ending logistical puzzle. And here's another thing to fear. Space is a vacuum. Mechanically, it's unforgiving. Imagine two polished surfaces touching, say, the inside of a joint or the edge of a clamp. Under vibration and vacuum, they rub together, and something called cold welding happens. They fuse. The surfaces friction weld into one solid piece. What was supposed to move gets stuck, can't rotate, can't deploy. A real issue with spacecraft mechanisms. Every hinge, lock, vent and clamp on the ship faces this risk. And ships need hundreds of these parts to work properly for centuries. The crew won't just be fighting normal wear and tear. They'll be battling weird space-specific problems that grow out of the vessel's environment. And when something fails, someone has to do repairs. Problem fixed, right? But in deep space, repairs aren't free. They come at a cost, and that cost is new risks. Every time a repair happens, the crew adds failure opportunities. NASA's reliability research shows this. Maintenance itself can create more problems than it solves if not handled precisely. You touch a system, you risk damaging it further. You swap one part and you might introduce a leak somewhere else. The act of repairing isn't just solving a failure, it's rolling dice with every system connected to it. This is the most important insight for generation ships. The crew isn't just fighting problems, they're creating new risks every time they intervene. Complex systems break in ways nobody plans for, And in deep space, the crew is dealing with ancient infrastructure, long past what it was designed to handle. Replace one valve, and a nearby seal might start failing next. But spares and repairs aren't the true horror. The real nightmare is what the mission demands. The mission isn't just about keeping a ship running, it's about preserving an entire civilization, a tiny, contained industrial world that can maintain itself indefinitely. Think of everything that goes into real maintenance here on Earth: tools, training, knowledge, materials. A generation ship has none of Earth's backups. It has no supply chains, and yet it must keep everything functioning. What kind of civilization do you need on board just to ensure repairs happen correctly? You need documentation, thousands of pages of manuals, manufacturing standards. Tools must fit tolerances exactly across generations. You need materials on science, understanding how metals age or how polymers degrade. You need apprenticeships. Workers must be educated, skilled, and trained in systems they didn't design. You need factories on board. Spare part fabrication can't rely on getting replacements from Earth. You need inspection protocols, people who can analyze microscopic cracks in parts before they break. You need error reporting, systems to make the repair economy transparent. And you need failure analysis, a constant flow of research into what went wrong, why it went wrong, and how to prevent it next time. Maintenance doesn't just require equipment, it requires culture. Skilled people across generations, constantly preserving the tools and knowledge needed to keep the ship from failing completely. A generation ship isn't just carrying a machine, it's carrying an industrial civilization in miniature. That's why the ship itself is impossible. You're not building technology to last forever, you're trying to preserve an entire cultural ecosystem on board, one that understands failure deeply enough to keep surviving for centuries. Without that, the ship doesn't grow old gracefully. It doesn't just slow down, it doesn't retire. It ages into chaos. Systems fail, spares dwindle, repairs introduce new risks, documentation gets lost, expertise dies with each generation that forgets why the old ways mattered. And over time, the ship itself turns into an unsupportable coffin, a monument to failed maintenance math. The truth isn't complicated. The crew of a generation ship wouldn't be explorers, they'd be technicians, constantly patching an aging, fragile vessel, fighting wear and drift inch by inch. And no matter how much they repair, time is always gaining on them. Every dream of a generation ship assumes one thing: infinite, reliable power. But spaceflight never works that way. Power systems degrade, margins shrink. The story isn't about abundance, it's about decline. And the numbers don't lie. Take the Voyager spacecraft. These deep space probes use radioisotope power systems, modern marvels in their time, but by 2025 they were losing about 4 watts of power every year. To save energy, instruments had to be shut down one by one. Now consider this. Voyager is tiny, no living crew, no need for constant heating, breathing air, food production or medical support. Shrinking power hurts a probe like Voyager, but it doesn't kill it outright. It just forces cutbacks. A generation ship can't make those choices. Power decline is survivable for machines, but for human habitats it's existential. A loss of power doesn't mean fewer sensors or slowed research, it means suffocation. It means spoiled food. It means lights and gravity failing. It's life support stopping. Human habitats don't coast gracefully into lower energy budgets. They collapse socially. Every watt you lose forces a brutal question. Who gets safety? Who gets rationing? Let's talk options. Solar power is usually the go-to for space systems, but in deep space, far from a star, solar becomes a joke. Sunlight follows the inverse square law. Double your distance from a star and sunlight drops by 4 times. Go far enough from any star and solar power becomes useless, unless you're building absurdly massive collectors. So what does that leave? The nuclear route. Radioisotope systems, maybe. Fusion reactors, if we ever crack that code. Maybe novel energy storage or generation techniques not yet invented. But all of these options come with a cost: repairs, replacements, decay, inefficiencies, and heat. Yes, heat. The ship won't just struggle to generate energy, it will struggle to cool itself. Here's why. A generation ship uses enormous amounts of energy. It's essentially a city floating through space. Powering lights for crops, keeping air breathable, running water systems, it all creates heat. And in the vacuum of space, there's nowhere for that heat to go. Earth can dump heat into the atmosphere or oceans. A spaceship can't. It has to radiate all that energy away. Waste heat gets dumped through radiators, and the bigger the power system grows, the bigger the radiators have to become. It spirals. Larger power systems mean larger thermal management systems. Larger thermal management systems mean more exposed areas vulnerable to damage. And more systems always mean one thing: more breakdowns, more repairs, more ways for entropy to push the ship toward failure. The problems here aren't just physical, they're cultural. Predictable power is survival. Losing that stability, that breaks societies. A civilization can survive hardship, but it can't survive chaos. On a generation ship, power loss feels like failure. It means failing crops, changing conditions, deferred maintenance, your safety net shrinking every day. Imagine this. The population on board doesn't just live in space, they live inside a budget. An energy budget, one where there's no getting more, there's only less, slowly, inch by inch, generation by generation, life becomes harder, leaner, uglier. And here's the kicker: power decline doesn't just hurt one thing, it hurts everything. No air without pumps to cycle it, no crops without artificial light to grow them, no clean water without purification systems, no radiation protection without active shielding, no diagnostics or emergency response without working electronics, no artificial gravity without rotating hardware. Power touches every part of life aboard. Lose 1% and it doesn't feel like a small problem. It feels like every system on board is running just a little worse, every safety margin a little thinner. The ship doesn't need a blackout to fail, it just needs consistent shortages, building up over time, turning once reliable systems into constant risks. Deep space doesn't kill a generation ship dramatically, it kills it slowly, not by pulling the plug overnight, but by making the effort to keep the lights on more expensive every year. And the worst part, there's no way to stop it. The crew isn't just managing systems, they're managing power decay across every subsystem, and no one on board will ever live to see a point where it gets easier. We envision the generation ship as an exciting future, a chance to explore, colonize, and thrive across the stars. But in that vision, we quietly avoided one devastating truth. The ship can never succeed unless it solves one impossible problem: reproduction. This isn't a mission for adults alone. It's not just sending trained scientists or astronauts beyond the Earth. A generation ship is built on a much scarier foundation. It's built on the assumption that humans can successfully conceive, grow, and live entire lifespans in conditions that aren't natural. That every life stage, pregnancy, birth, childhood, puberty, aging, will happen just as it does on Earth. But space doesn't care about your biology. And deep space is nothing like Earth. The standard question for astronauts is simple: can an adult survive and function in space? We've answered that one, at least temporarily. Yes, adults can adapt. They can train to overcome bone loss, muscle atrophy, or radiation. They can live months, maybe even a year in zero gravity. But that's not what a generation ship demands. Instead, the mission asks a far more dangerous question. Can an entire human life cycle proceed normally in space? Can embryos form without deformities? Can children grow? Can their bodies handle the stress of radiation, artificial gravity, and confinement? And most terrifyingly, will their genes survive intact enough to safely pass on to the next generation? This is uncharted territory. Human reproduction is a delicate, extensively coordinated biological process. and our understanding of how it works under spaceflight conditions is razor thin. What we do know isn't comforting. Radiation alone throws the entire concept into chaos. Let's start there. Ionizing radiation is deadly, whether it's solar particles or galactic cosmic rays. On a short mission, it increases cancer risks in adults. On a generational scale, the stakes become far worse. Radiation doesn't just damage your body, it attacks your DNA. One key vulnerability is the gonads, home to sperm and eggs. These cells are sensitive to radiation. High-energy particles can disrupt their normal function, introduce mutations, and damage hereditary material. And while adults might endure the effects, their children's entire genetic foundation could be compromised. Radiation means heritable risks. It could destabilize the genomes of entire future populations, introducing medical problems and developmental disorders that steadily worsen over time. A design that might work for today's crew could be completely unsafe for their descendants. The ship isn't just transporting astronauts. It's supposed to protect humanity's genetic line for centuries, and that requires a radiation environment Earth-like enough to avoid permanent damage. Deep space doesn't offer that. Beyond radiation, gravity raises a different set of dangers. Human reproduction has only ever occurred in one gravity setting, Earth's. We know embryos develop with specific pressures, loads, and fluid distributions. Microgravity eliminates those cues entirely. Without weight forces guiding cell and tissue development, it's uncertain if embryos can implant, form correctly, or differentiate into functioning organs. Even artificial gravity, like spinning the ship to generate downward force, isn't guaranteed to solve the problem. Spin radii, gravity gradients, and Coriolis effects all interfere with how the body perceives and reacts to its environment. If gravity feels inconsistent or pulls on different parts of the body in conflicting directions, it could disrupt the process. Growing up under altered gravity means childhood development would be an experiment, not a certainty. Circadian stability adds yet another variable. Circadian rhythms, our biological clocks, time countless processes from sleep cycles to hormone release. On Earth, sunlight reinforces this rhythm. Morning means bright light, blue wavelengths. Evening means dimmer light. What happens when the ship doesn't have natural sunlight? Or worse, what happens if its artificial day-night systems break? Circadian disruptions are already tied to stress, metabolic disorder, immune dysfunction, and fertility problems. It's not enough for the ship to support life. It must support normal rhythms across generations, consistently with no failures. And then there's stress. Confinement, isolation, monotony. Living on a ship means psychological pressure that Earthborn humans aren't built to endure. Stress directly harms fertility and has ripple effects across entire populations. If stress alters hormone levels, interrupts reproductive cycles, or weakens community cohesion, the ship could slip into a spiral of declining births and rising instability. Here's where it gets even more bleak. We have massive evidence gaps, giant holes in what we know or can predict. To date, no extended human reproduction has been studied in space. None, not even a single pregnancy. No multigenerational data. The only insights come from small-scale studies on animals, analog habitats, and theoretical reviews. Some experiments suggest microgravity disrupts normal reproduction in mice, but mice aren't human, and every assumption about humans is still guesswork. This makes the concept of a generation ship reckless. The mission doesn't fail because we've proven it won't work. It fails because it demands betting humanity's entire reproductive future on questions we can't answer. The term generation ship feels like a damning kind of lie. It assumes the hardest problem works, that reproduction is stable, development is normal, and genetic health remains unbroken over endless generations. Those assumptions aren't engineering details. They aren't small obstacles to tweak or troubleshoot. They are the foundation of the mission, and they rest on nothing but wishful thinking. We know reproduction struggles on Earth's toughest edges. High altitudes affect pregnancies. Stresses in disaster zones disrupt fertility. Low-resource environments increase rates of complications. Now imagine all of that turned up exponentially, confined to a deep space habitat where life support never stops wobbling on the edge, where genetic damage quietly builds up, where every birth happens under conditions humanity evolved to avoid. The hole at the centre of this concept is the simple reality of time. The data we need to prove generational reproduction works in space would take decades, maybe centuries to gather. We'd need experiments that stretch far beyond Earth, controlled studies, multiple generations tracked from conception to maturity. But here's the cruel fact: by the time you have that data, any generation ship project would already be dead in the water. A generation ship doesn't just ride through deep space, it carries a biological gamble so fatal it makes every other engineering question irrelevant. You're not designing a vehicle, you're designing an artificial womb for all of humanity, packed with systems that must sustain genetic health and development without faltering for hundreds of thousands of people, across centuries. The future isn't a bold, adventurous idea. It's a fragile, reckless leap with no landing mat. Until we solve reproduction in space, there is no generation ship. There's just a concept that collapses under its own wishful weight. When people imagine a generation ship, they picture teamwork, a focused mission, a strong, united crew working towards survival. But reality is messy, and people, no matter how committed they start, don't stay frictionless. A generation ship isn't just a test of engineering, it's a test of sociology. And sociology doesn't follow simple rules. Now imagine this: a ship population confined for decades, families forming, children growing up in metal walls, factions developing, resources slowly dwindling, conflicts brewing. What does a society look like after living through this for 3 generations? 4? Do they stay united? Or does the ship itself become a prison of endless human problems? We already have some brutal hints. Mars 500 was one of the longest Earth-based confinement simulations ever performed. 6 men, 520 days, a habitat of 550 cubic meters, about the size of a modest house. The people selected were highly trained, hand-picked for endurance, monitored carefully by experts, but it only worked because it was temporary. Even then, issues surfaced. Psychological strain, stress, social tensions. These weren't random civilians. They were highly capable participants following a clear short-term plan. Now imagine swapping them for an entire multi-generational population. People of all ages, people with no escape, with no finish line. A generation ship isn't full of astronauts. It's full of humanity. It includes children, the elderly, subcultures, outliers, and people born into the mission without any choice. Arguments aren't small, grievances don't fade. Suddenly the question isn't just about survival, it's about maintaining a society that doesn't break in half. Even basic habitat volume is a clue to the limits of human tolerance. The Mars 500 team survived in 550 cubic meters, around 19,400 cubic feet of space. It works for controlled experiments, but for a generation ship, that's survival, not thriving. Can humans endure confinement? Is not the same as can humans build a civilization in confinement? One is hardship, the other is normal life stretched across centuries. Civilization isn't built on walls, it's built on purpose, stability, and space doesn't have enough room for all of that, not at the scale we need. People need space to separate, to socialize, to express themselves. But the bigger your ship grows, the more mass you have to haul, the more shielding it needs, the more power, food and resources the journey demands. Thin margins get thinner. Any imbalance, no matter how small, rattles everything. Now imagine this scenario. The ship runs into a governing crisis. Something changes. A divide forms. A new faction starts gaining momentum. Who fixes it? On Earth, nations can watch each other, intervene, guide, correct. But in space, distance kills oversight. Communication delays aren't measured in seconds, but years. If your generation ship is headed for Proxima Centauri, that's 4.25 light years away. Even a desperate plea for advice would take more than 4 years to reach Earth, and another 4 years to hear the response. Meaningful advice turns into delayed archaeology. By the time new instructions arrive, the situation on the ship has completely changed. This is critical. Long-distance space travel doesn't just cut off real-time corrections, it creates isolation. The ship becomes sovereign, its own experiment. Rules, norms, and plans made on Earth slowly lose shape. People start experimenting with new ideas of governance, life, and technology, and drift happens. Governance failures on board can't be fixed from Earth. Small problems like favoritism, inequality, or resource fights snowball. Factions turn into entrenched groups. Entire generations of shipborne humans grow up with no memory of the original mission. Historical amnesia sets in. People forget why the journey started. And it gets worse. Cult formation becomes more likely in isolated populations. A single influential leader can steer the ship down an entirely new social path. On a contained vessel, those shifts can override logic, compromise life support, or destroy years of cultural stability. Suddenly, the ship isn't exploring space anymore. It's negotiating crises, one after another. This is where the generation ship fantasy collapses hardest. It imagines transportation, moving a healthy group of humans from one star to another. But in practice, the ship's story transforms. It's no longer about travel, it's about managing a drifting civilization trapped in finite boundaries. And here's the scariest part. A ship's survival isn't just about machinery. Every life support system requires trust. Emotional bonds affect discipline. Law keeps repairs organized. Culture keeps morale steady. When societies fracture, the tools they maintain fracture with them. If a bridge fails, cars stop. If a society on a generation ship fails, survival itself begins to unravel. Pipes leak because people stop checking. Crops die because plans break down. Expertise disappears because teachers lose students. Every technical system aboard depends on human cohesion. You don't just lose rules, you lose air, food, maintenance. Every system needs cultural stability to keep human hands working. But over centuries, cultural stability gets harder to preserve. A generation ship sounds ambitious, a marvel of human engineering, a triumph of will over the void. But this idea isn't just hard, it's impossible. Not because one thing will fail, but because every system on board depends on another. When one fails, the others begin to topple. This isn't a problem of single points of failure, it's a problem of interconnected weakness, and that makes it unsolvable. Radiation breaks through shielding. Shielding makes the ship heavier. A heavier ship needs bigger engines. Bigger engines need more fuel. More fuel adds weight again. Weight pushes maintenance requirements through the roof. Maintenance eats into spares, and spares rely on storage, energy, and perfect logistics. Radiation also hits people. It weakens their bodies, damages their DNA, hurts their immune systems. Sick or stressed people make mistakes. Mistakes hurt systems, systems falter. And stress builds up among the crew and life support feels shakier every day. Things don't just fail on their own, they pull each other down together. This is the real reason generation ships can never work. The systems don't stay separate. Every subsystem on board depends on another, feeding new challenges into an endless loop. And the entire ship's design makes this worse. It isn't a simple machine, it's not a closed box, it's a non-linear system. Small problems don't stay small. Biosphere 2 proved this back on Earth. Biosphere 2 was a closed environment experiment. On paper, everything was calculated to work. Oxygen, carbon dioxide, soil, plants, animals. But the system drifted. Microbes in the soil overbreathed oxygen. Gas levels fluctuated. Carbon dioxide surged. Concrete absorbed molecules unexpectedly. In the end, the system didn't break apart in one loud disaster. It slipped, slowly. The chemistry fell away from the plan. A subtle, creeping misalignment that killed the viability of the habitat. That's how the closed systems on a generation ship would break too. Chemistry, biology, physics, they all interact in ways we can't fully model or control. And that's before you stack decades or centuries of operation into the equation. A single cosmic ray flips a bit in a computer. A slightly degraded filtration system lets moisture into the wrong air duct. A power fluctuation shuts off crop lights an hour too soon. That's how problems snowball in nonlinear systems, not in a blaze of fire, but through constant drift toward chaos. You might think, just add redundancy, add backups, extra safety margins, extra spares, but redundancy gets its own price tag. Redundancy means adding mass to a ship that's already struggling with weight. More backups mean more interfaces that need inspecting, more moving parts that need servicing. Spare parts don't arrive for free. The more redundancies you build in, the more failure points you also introduce. Redundancy doesn't erase risk, it moves it to new places. And who maintains all those redundant systems? Generational crews will, but people strain under the load of precision, training each generation to maintain every redundant layer perfectly. That isn't manageable, it's a myth. The system becomes too sprawling to control. This pattern always comes back to one ugly truth: we'll solve it later doesn't work, not in deep space. Let's look at examples we already have. Food on the ISS, decades-old space probes, astronaut biology. Every detail paints a grim picture. ISS food breaks down after a few years, vitamins degrade, nutrient levels fall below critical standards, storage can't keep up with multi-year quality. Voyager's power systems drop wattage every single year. Instruments shut down one by one. Energy doesn't stay constant. It bleeds out. Astronauts lose bone density in months. This isn't hypothetical, it's happening now on low Earth orbit missions. Multiply months by decades or lifetimes. The damage becomes irreversible. These aren't just small problems, they're accumulation problems. Each case points toward one conclusion: the environment wins, slowly but unavoidably. On Earth, civilization survives with constant fixes, resources, maintenance, external reinforcements. A generation ship doesn't have that. It has no reset button, no tanks of liquid oxygen waiting outside, no engineering teams ready to fly in with replacements. For a generation ship to succeed, it would need to be better than any society humanity has ever built. Not just technically brilliant, but culturally bulletproof, technologically advanced, medically resilient, ecologically literate, manufacturing capable. All of it has to hold steady over centuries, in a place where the margin for error is zero. The ship would need to train its crew perfectly every generation, pass knowledge down without gaps, preserve institutional memory. That alone is a staggering challenge. Skills get lost, cultures forget. Even on Earth, civilizations fracture and fall apart under pressure. Space amplifies that, because every crack in knowledge translates into a bursting pipeline, a broken air pump, or a failed crop yield. Think about what that failure means. A single missed training session could ruin critical protocols. A small loss in education might wipe out the ability to fabricate parts. And here's the harshest truth: none of these problems stay isolated. Deep space isn't waiting quietly for one solution to emerge. It's hitting the ship from every angle at once. Every system stretches thinner over time. Radiation poisons people and hardware. Shielding weighs the ship down. Weight taxes engines. Engines demand fuel. Maintenance burns spares and energy. Power declines. Declining power makes food systems fragile. Fragility spreads stress. Stress disrupts society. Everything feeds everything else, and it all points in the same terrifying direction. The system eats itself alive. A generation ship isn't crossing between stars. It's an artificial world trying to stay alive in an environment fundamentally incompatible with human life. The final answer isn't subtle. It isn't pleasant. A generation ship doesn't just sound impossible. It is impossible. Because deep space doesn't challenge one thing, it attacks everything at once. You're not carrying a ship across the stars, You're trying to freeze a piece of Earth inside a synthetic shell while the universe shreds it layer by layer. That's not exploration, that's entropy winning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.